Okay, division of complex numbers. Now this is why we need to know how to do the complex conjugate. Now, have a look at this. We've got 8 minus I over 2 plus 3i as an example. Now what you do, ladies and gentlemen, is you rationalise using the complex conjugate of the denominator. So how do you do that? You multiply top and bottom by the complex conjugate of the denominator, okay? And what that does is something truly amazing. I will show you. We get, multiplying this whole beastly thing out, we get 8 times 2 is 16, minus 24i, minus 2i, and then plus 3i squared. Now, of course, I squared is minus 1, so this little beastie becomes minus 3. So, in fact, if we work that out, what do we got? We've got 16 minus 3, and then we've got minus 26i. But what's more important is what's going on the bottom. Okay, the denominator becomes, by rationalising with the complex conjugate of the denominator, you get a difference of 2 squares. That'll turn into 2 squared minus 3i all squared, which will get us 4 minus 9i squared, which becomes 4 plus 9, okay? And that gets us a rational denominator, which is what we want when we divide two complex numbers, okay? That's what happens. You get a rational denominator, and that's the way they want you to write it. They don't want you to be left with a complex number on the denominator. That's the whole purpose of rationalising using the complex conjugate. And so meanwhile, back at the ranch, we can simply divide through top and bottom by 13, and we get that. That's the answer. Yep, it looks a lot nicer than this, I'm sure you'll agree. So now you know why we use the complex conjugate. Yeah, it's very nice, isn't it? Alright, some examples for us. Here's Z1 and Z2. Now what are we asked to do? We're asked to show that the conjugate of Z1 plus Z2 is equal to the conjugate of Z1 plus the conjugate of Z2. Alright, let's just see if we can prove that. Now, Z1 plus Z2 is equal to this, which is very easy to work out. It'll be 5 minus I, okay? Now, the conjugate of that, of course, would be 5 plus I, okay? So that's the left-hand side of this equation here. Let's have a look at the right-hand side now. We know that Z1 bar, if you look at it, here's Z1, would be 2 minus I, and Z2 bar would be 3 plus 2i. Now, we're going to add them up and see what we get. Okay, looking very exciting. We just get 5 plus I, so we know that this is the left-hand side, this is the right-hand side, and therefore we've proved that the left-hand side equals the right-hand side, and we're laughing, guys. Yeah, it's pretty good, isn't it? It's marvellous. Okay, here's another example, just to get us used to all this complex number stuff. We've got Z equals C plus ID. We have to express in terms of C and D, Z times Z bar. Alright, and secondly, Z over Z bar. Well, no problem, guys. Let's just go right ahead. So Z times Z bar would be that, and that looks suspiciously like a difference of 2 squares to me. So it's just going to be C squared plus D squared. Ah, very nice. Yes, did you get that? Because minus I squared D squared is plus D squared, because minus I squared is plus 1. You getting it? Great. Okay, what about B? Okay, Z over Z bar, no problem. We're just going to do a little bit of rationalisation throughout the nation. We'll multiply top and bottom by C plus ID. And when we multiply all it out, we're going to get... Okay, I've just simplified it a bit. It's C squared minus D squared. That was going to be plus I squared D squared, which is just minus D squared, plus 2CDI over the difference of 2 squares, which gets us, we're getting used to it now, C squared plus D squared, and that's our answer. Yes? Great. Another one for us. Okay, we've got Z equals X plus IY and C equals E plus ID. Show that, good heavens, show that Z minus C times Z bar minus C bar equals R squared is the equation of a circle with centre E and D and radius R. Now the reason that I've put this one in is that this is a VCAR favourite. They put this in the VCAR bulletin a few years ago, and then this popped up on the exam that year. So I want you to get used to the idea early on that if you see this, you are looking at a circle. Okay? Z minus C times Z bar minus C bar equals R squared is a circle, guys. Okay? Is a circle. Let's just go ahead and prove it for you now so that you can be convinced. Now, C was E plus ID, wasn't it? And Z is X plus IY. Let's just flesh that out a bit. Okay, have a look. Z minus C, Z bar minus C bar equals R squared. Okay, let's go for it now. We're going to just clean up inside those brackets a bit now, combine the reals together and the imaginaries together. See if you agree with me. That's X minus E plus I times Y minus D. That's right. That's X minus E. Now if you just look very closely at this, it does correspond to what's there. So that's going to be minus IY. That's okay. And this is going to be plus ID. And so minus times the minus gets you a plus, yeah? Okay, great. Now, the marvellous thing about this is you've actually got a difference of two squares. Look at it. It is, isn't it? So therefore it's very easy for us to then rewrite that left-hand side stuff there as that. Yeah, very nice. And then we can rewrite it, getting rid of the I squared term, as plus Y minus D all squared. And look, we're laughing. We've certainly got a circle with centre E and D. That's the X and Y coordinates, respectively, and the radius is R. No problem, yeah? What? We've got some more here. Okay, example 4, what does that say? Express in the form X plus I, Y, those things. No problem, this is just good old practice for us, okay? So with A, what I would do there, ladies and gentlemen, is I would just multiply top and bottom by I. No problem, because that's going to rationalise the denominator very nicely, because I squared on the bottom is minus 1. So we get that, and that turns into that, yeah? Very nice. So let's go for B now. Well, we're just going to rationalise the denominator. You know how to do that now. We just take this one and find its conjugate, multiply top and bottom by it, and what do we get? On the top, we will get 9 minus 6i plus I squared, which of course is minus 1. So we're going to get 8 minus 6i on the top, and we're going to get 9 plus 1, which is 10 on the bottom, and there'll be a little bit of cancellation, I think. Yes, we can divide through by 2, and we'll get 4 minus 3i over 5, and put a blue box around it, and it's great. No problem. Now, what about this C? That looks like a pretty nasty little customer. No, not really. Just multiply out the bracket, and it'll make it a lot simpler, I think. Yes, that's right. It's just going to be 3 minus I over 4i minus I squared, and of course minus I squared is plus 1. So I've just rewritten it with the real bit first and the imaginary bit next. Okay, all we've got to do is rationalise that in the way that we have now become accustomed, and it'll all come out in the wash for us. So what is it? It's going to be 3 minus 12i minus I plus 4i squared, which is minus 4, over, difference of two squares, remember, 1 minus 16i squared, which is plus 16. Okay, now let's just get all our ducks in a row and clean this up a bit. 3 minus 4 is minus 1. This is minus 13i over 17, and everything's lovely. Blue box, please. Very, very nice. Yes, you're happy? Yes, I'm happy too. Now this is just how to do it on the CAS device. Okay, it's really a snap on the CAS. If you do this sort of thing on your CAS device, it'll just work it out beautifully for you. Yes, this one, this is in the previous screen. Very nice. And it also knows things like conjugates, yeah? And for that matter, real parts and imaginary parts, yes? So everything's good. Yes, do you see the light? Yes, I see the light too. All right, that was fun. I'll see you soon.